Hello everyone, thank you for joining this tNavigator webinar hosted by Rockflow Dynamics. Today's session will be presented by Marcus, geoscientist from our Aberdeen office, and Serkan, senior reservoir engineer based in Germany. Our colleague Andreas from the Perth office also contributed to this presentation, but unfortunately he couldn't join us today. This is the last part in our current webinar series. If you would like to see the 3 previous webinars, they are uploaded to our YouTube channel. In today's session, Marcus and Serkan will demonstrate how to use probabilistic assessment techniques for CCUS modelling. Everyone who's joined the webinar has been automatically muted. If you have any questions, you can type them into the chat box on your screen and we'll answer as many as we can at the end. If we don't have time to answer your question live, we will follow up with you on the email. We are recording this session and we'll upload that to our YouTube channel as well, along with the others. Thank you so much, and I'll now hand over to Marcus to begin the presentation.
So, hi everyone, how are you doing? I'm Marcus, based in the Aberdeen office in Scotland. And delighted to speak to you today. I'm just going to switch off my camera so there's no kind of lagginess, but I can come back on at the end for questions. Okay. So today we'll be talking about tNavigator and how we can use this to better model our CCS projects, in particular looking at modeling probabilistic migration pathways for plumes. So if you didn't know, tNav is a fully integrated software package which allows us to do everything from our static modeling to our dynamic modeling, as well as surface network modeling. This is all housed within one package. It's using the same code so it can speak to itself seamlessly, which means integrated teams can work together in one interface. I think there might be a bit of lag in changing the slides here. Let me just see. Okay, so where are we with CO2 storage? Well, as we know, it's one of the main methods that we'll be using for capturing CO2 and meet our net zero targets. I did this schematic here was a placeholder. I was looking for some detailed notes on how much we've done today and where we are, but it turns out these numbers aren't as easy to find, and this is partly because the ongoing projects at the moment maybe report in different ways. And often we discuss the capacity as opposed to the actual stored amount. Some good papers by Zhang and Jackson and Crever back in 2022 estimated about 200 million tons of CO2 has been stored to date. However, when we look at what's maybe going to be happening in the UK in the future, we've got 75 to 180 million tons stored per year predicted for 2050, so quite a lot more. So we have a long way to go. There's a great website called co2storage.co.uk. If you've not been on it, I can highly recommend it. I think it's one of the first countries to release this kind of database, which allows you to look at the potential storage sites for the whole of the UK continental shelf. When we and they estimate there's 78 billion tons of CO2 storage capacity. When we look across to Europe, we can see there's around 36 projects in the pipeline. The ones in bold marked on this map from the ILGP are the projects that are currently ongoing. Of course, we've heard of projects like Snowvit, Sleipner, and Greensand. They predict by 2030 that we should be able to store 110 million tons of CO2 per year. So what does this all mean? It means that we've got a long way to go, and this means we're going to have to do a lot more CCS modeling. Not only do we have a lot more modeling to do, but also this modeling is more complex than ever. When we look at the guidelines from the North Sea Transition Authority in the UK, the NSTA, and also the EU CCS directive, the requirements don't only require us to model out these CO2 storage sites where we're planning to put the CO2, but also the storage complex. So there's a nice diagram here from the Reservoir Model Design book by Phil Ringrose and Mark Bentley. I can highly recommend it. And this just gives an illustration of the area we're looking to place our CO2, but also we have to understand the wider complex. So this is the storage site, but also all surrounding geological domain, which can have an effect on the overall storage integrity, so potential secondary containment and where this might go. So when we're injecting CO2 into the ground, essentially we have a good grasp of where this plume will go. So probabilistic modeling is a very effective way to understand what's happening away from our wells. This will allow us to more confidently understand the range of uncertainty involved in these CO2 prospects. So today we'll be looking at tNavigator and how we can use this to better model our CCS workflows. So just to give you a quick overview, we can see we have our geology designer on the left there. This is our static modeling domain. We have model designer, network designer for planning our pipelines and our injectors, and then we have our simulation, and we have uncertainty engine to understand the uncertainty across all aspects of these projects. So the different stages of CCUS, we have capture, and so this might be more from an industrial process, so steel and cement production plants, also power plants, and more advanced technologies like direct air capture. This is where we're capturing the CO2, and the aim is then to transport it and store it. So this could be transporting through pipelines, and then we're looking to store. Most of the environments we're looking to store and talking about are either depleted hydrocarbons or aquifers. And also we already do and looking to continue to enhance oil recovery as well by storing CO2 in the ground as with existing production. The final stage is also injection, so facility and well design. How does tNav come into all of this? So we can come in from the transport point of view, so looking at the fluid modeling with our PVT designer, pipeline modeling with our network designer, and then really as a geoscientist where I might come in, and also Serkan as a reservoir engineer, we're looking at storage and utilization. So using geology designer, our modeling designer, our rel perms, our PVT, and our uncertainty, we can do our geological modeling, fluid modeling, reservoir modeling, geomechanics, uncertainty, and optimization. And also from the injection side, we have well modeling and fluid modeling. So this allows us to model all aspects. So big questions for CCS modeling: how much can we store? So what's the capacity? How long will it be stored there for? Will it be contained, and for how long? So this is where our dynamic models become really important. We want to model these over the lifespan of the project, but also hundreds of years into the future to ensure that when we're storing it, we're confident that it's been stored permanently. And more from the topic of today is how will the CO2 plume behave? This is controlled by our geological inputs, where the static modeling comes in, but also how the fluid is going to behave and how we model that physics. So within tNav, understanding how this plume will behave and how it's stored, we can already model things like structural trapping by creating our geological static models and understanding the pore volume and how it will move through the reservoir. We can do residual trapping. So this is where heterogeneity isn't necessarily our enemy, but can be our friend. So getting a good grasp on that and modeling it accurately based on the information we have throughout our reservoir is really important. Solubility trapping and also mineralization are all possibilities within tNav and will be very important for understanding the volumes that we can potentially store in the subsurface. It's also equally important to understand, can we keep it there? Modeling the rock failure and the geomechanics is necessary to understand the pressure that's being impacted on the sealing rocks, that we can safely store the CO2 in the storage site permanently. And we also want to understand if there's any effects on this seal or faults or existing wells in the vicinity. We also have the ability to have to model our wells and also our surface pipelines. We have a full implicit coupling solution for the network. This means we can design and model our surface network, the injection and transport of CO2 into these facilities. So it's a complete full asset modeling package. So all of this is integrated within tNavigator. It allows us for easy variable definition from each part of that, from the static side, the dynamic side, and also the network side. We've got extensive algorithms that allow us to do this, and then we can easily ascertain our results and understand the full range of uncertainty and the size of the prize that we're looking at here from our result analysis from our uncertainty engine. So integrated software, integrated workflows. This is a little diagram on the left there that I like, again, from the Ringrose and Bentley book. And it basically discusses the sequential approach, which was maybe the default workflow for energy companies in the past, where we receive our data, we get our seismic, our petrophysics, our well data, and we begin to build up a static model. And then that, as time continues, that's finished and passed on to the reservoir engineer. He continues his work. However, what Ringrose and Bentley point out is the dividends and time saved by working in a more parallel approach, where we continue to update our ideas and our models as we're working together. So we can go backwards and forwards between the dynamic and static range, and this allows us to understand those uncertainties more quickly, because we understand the questions that each team member from different domains are trying to answer. On the right there, you see some of the workflows actually we'll be discussing in the demo today. So just flicking through those. And these are workflows that have been added to by a geoscientist and the reservoir engineer, all working in the same software, in the same space. And this allows very good communication to understand all the kind of details of the project. The image on the right there is an example from earlier in the year. We were on the northeast of Scotland with Mark Bentley, myself there in the blue jacket, and also Serkan, who'll be speaking later, closer to the beach. We're looking at this geology, and by being in the same room, by being in the same software, by being in the same by being in the field together, it allows us to think about what questions are important to each aspect. So not just think about the geology from a geologist perspective, but also how the fluid would see the geology. And this is important as we think about CCS modeling. So I'm going to be looking at the static part of the package. On Tuesday, we had a great presentation from John and Jordan that you can find on our YouTube, which really goes into more detailed workflows, what we can do within Geology Designer. Today, I'll be going through the actual workflow and how we can add uncertainty to our static model, and Serkan will continue within the dynamic model. And this is important. The storage capacity and plume migration is strongly controlled by geological factors. When we build a model, we have lots of information at the well and the core, but then we rely on model building to understand what's happening in the interwell space. This is based on our concepts of geology and the deep superficial environment, structure, mineralization. So getting the modeling right to match our concept is very important. Understanding our uncertainties from a geology point of view is important. So what's our structural uncertainty? This can affect our storage capacity. This can affect potentially our storage site. So that's the area that we're looking to model, if there's enough flex on these horizons away from a well, if we're not certain with our velocity modeling. What's happening in the interwell space? So how do these reservoir properties change? Maybe we know what's happening at the well, but away from that, it's important we understand all possibilities to accurately ascertain the possibilities to how these plumes could migrate and what's the connected pore volumes. So now I'm going to go into the software, and we'll have a quick look at just moving through this workflow, building up a deterministic model and adding variables to this, so then we can run it multiple times and understand equiprobable realizations of our model. So this is the data we're working with today. We have two zones, likely a depleted field. We've got a lot of well data here as opposed to an aquifer, but with an aquifer, the ability to probabilistically model is even more important. You can see some well data here. We've got porosity, sonic, beach shell, a lithology log. We've got a right-hand toolbar on the right there where we can get a bit more information from our cross areas and just look into that data in a bit more detail. As we move back to our 3D window, we're going to open up the workflow, and this is a workflow that I've created, and it allows us to rerun models quickly, update models as we get new data, and also this is the home of where we can put in all those variables, so we're not just creating one but a bunch. So here we've just created an error surface map. We can control the spatial variability and also the variability up and down. So whatever you think the error on your surface is, and we can apply this to any of our horizons. Here we've just done the top surface horizon. We then smooth that, and we apply it to our top surface to correct it, and then we readjust it to our well data, our well tops, our markers to correct, and these will be inputs into our grid As we move into the grid building, we can throw in our horizons and our markers, define the layering type, and see how that layering looks. In this case, just the 2 zones. And then we go on to take that world data that we just viewed, and I'm going to quickly block it here, and then we can upscale this to the whole model. So this is our lithology that we've blocked, and again, we'd want to QC this with our histograms and our crossplots that you can see in tNav to make sure that we're accurately representing the data that we see in our logs, our V shale, and then our porosity. So now we can take this and use it as inputs to our fasces modeling. You can see in the case on the left there, we've got 4 instances of this Gaussian simulation. We've got variables already stuck in here. So these variables I'll show you at the end where we define these. And so we could run maybe 4 different concepts of this model. And we could run them in different instances and see what the results are. So if we just look through some of the properties we create for this grid here, this is our fasces model, sand being in yellow and shales being in brown. And we're looking at different realizations of this model. So as we move through that, we can see how probabilistic methods and modeling with our interpolation algorithms can have different realizations in cases where we can see our sands are completely connected, but between different models, we have higher porosity layers and then layers that are less well connected. So just jumping through the different properties that we're looking for the geology here. So our V shale with the yellow in here being high V shale and permeability. So again, you see each model might have a different permeability streak. This will affect how the plume migrates and moves through the model. It's just as important to model each of these so we can have a better assertion of what's happening net to gross. Potentially your net to gross definition might change depending on where you're placing the CO2 and also what phase it is as you're importing it. So it's important to have variables for all of these inputs. Our pore volume here, again, you can see it changing depending on the different inputs to these models. And we can also output a connected volume. So it's just a discrete parameter where it shows which parts of the geology are connected together. And this is a good way to see what parts of the geology may speak to each other. So now going back, we next want to create an extended grid so we can start to do some geomechanics. So in this case, we're just going to do it for our cap rock, but you could take this all the way up to the surface and model geomechanics for the whole overburden. So here we've just thrown on, extended that grid there to create a cap rock. And we run some calculations to apply some properties to this as well, just very quickly within the workflow. All of these could have variables, so we can have multiple iterations of what this may be and the properties that this may have. So just again, flicking through these different properties here, you can see that for some of them we've applied those new values. Okay, now going into some geomechanics. So we have the ability to apply our geomechanical properties to each of our different lithologies. So the filter values there are the lithologies, and we can apply Young's modulus, Poisson's ratio, the cohesion and theta properties to each of these. And then using the calculators, we can run all of those and apply it to our model. So here we can see our Poisson's ratio adjusted to porosity, our Young's modulus adjusted to porosity, and our tensile strength, just as an example. Now looking at our input variables, so what you saw there was more or less creating a deterministic model, maybe with a few concepts of our fasces, and this is where we can begin to add in the variability. So you'll see from the top left there, we have our error maps. This is where we could change the variability on our error surface. We can change the seeds, so there's a bit more variability, and we can apply min and max values. We can define the distribution type for our varograms, which can affect how our geobodies may be connected. And again, we have a bunch of variability that we can apply to our geomechanical properties. So when we run this within our uncertainty engine and run it hundreds of times, we'll take different values each time we run our model, which allows us to have a much better understanding of the probability for different scenarios that is out there, because obviously we don't know exactly what's happening away from our well. This allows us to do so. So as a geologist, this is me done my job. Next, I can pass this on within the same software to our reservoir engineer, Serkan, and he can continue to build up see what I've done. The workflows are recorded there, creates a nice audit trail, and he can continue to add his fluid properties and how the CO2 will behave as he begins to simulate this. And so now I'll pass on to Serkan and give you control.
Thank you, Marcus. Let's see if this works. Yeah, seems to be working. Okay, so continuing the workflow from where Marcus left off, I'd like to briefly talk about some of the different types of variables that we use here for the dynamic realm. So on the first part that we can see is sand perm, silt perm, shale perm, caprock, H and V perm. So the last two are explicit permeabilities for the caprock, both in the horizontal and vertical direction. And the first three are exponents for the different reservoir facies that Marcus has already demonstrated before. The next set of variables would be relative permeability parameters in the Corey system, so the critical water saturation, the critical gas saturation, and the exponents for water and gas systems. And at the bottom, we have injection rate and pressure parameters, as well as the top perforation depth and the perforated interval. So for each case generated, we're actually also changing the injection scheme. So just to illustrate this point a little bit more, on the left-hand side we have a cross plot with a logarithmic y-axis showing permeability, and on the x-axis we have porosity. Just as an example, the sand that can be seen on the top left part, the line that is kind of light orange. We see the equation that was used to generate the permeability property for the sand facies here. And you can see here this variable that is enclosed within the @ sign. So that's one of the variables that is actually changing this relationship. So on the right-hand side, we have the relative permeability. So we're moving this critical water saturation left and right ever slightly, and the same for the critical gas saturation, moving this point, and also changing the slope of this, or the curvature of these lines. So once we've set up the dynamic properties that we need, and we have run the workflow once, we can actually just run the base case and have a look at it. So in our base case, we first would like to look at the graphs. And here I have a stack plot showing the events as they happen. So here I have injection starting in 2023, followed by stopping of the injection due to seal breakthrough in 2039. So this is done automatically with a Python script that checks for presence of gas in the caprock. And we still run it for a while until 2220s. Just to see the effect of the different trapping mechanisms. So this is the next thing I want to show. Because it's a stack plot, you can see, for example, dissolution trapping at the bottom, and from here to here. So this amount denotes the residual trapping, and the last part is the structural trapping, all of which put together is the total CO2 injected that is stored in the reservoir. And you can also see that in between the time that injection was stopped and the end of simulation, we actually we would expect the CO2 plume to migrate further. We don't see it in this plot yet, we'll get to it. But what you can definitely see is the redistribution of the different trapping mechanisms, which I tried to make a bit more clear in this non-stack plot. So these are all the different parameters that I've shown before, but not in a stacked way. So you can directly see on the top the total CO2, residual trapping, dissolution trapping, and what's missing here is the structural trapping. So moving on, we've looked at some nice graphs. We can look at some 3D properties in cross-section. And here we have the pH value on the top. We have the CO2 solubility in water in the middle pane, and at the bottom we have the CO2 molar density. Ever slightly different depending on how the contour lines are generated here, but I guess it depends on your needs, how you want to set these views up. But this is also a nice way to see what is happening with our plume. Well, bear in mind, this is still just the base case. So again, looking at the base case, we can generate a filter property based on either molar density of CO2 or gas saturation, or however you want to look at it. And with that filter, so I can just repeat this. With that filter that you can see here, we can get a 3D visualization of the plume. We can get a 2D visualization of the same property. And over here, we have the molar density of CO2. In this view, you can also see the extended grid. So this is due to the geomechanical properties that we've added. And I've adjusted the transparency a little bit so that you can actually see into the reservoir, which is what we want to look at, which is the plume. Additionally, you can see the perforation interval for this particular base case. So, so far all good in terms of post-processing and analysis and visualization of our results. But again, we're just looking at one particular case. So the idea is to run the workflow and generate 200 or more, depending on your needs, different runs to look at a sensitivity experiment. In this case, we've run 200 cases using Monte Carlo. You can also use Latin hypercube, or we have other algorithms that you can use if you're interested. The point is we can now continue to look at the graphs as we did for the base case, but for a multitude of runs. And over here, I've plotted the total CO2 injection versus all the different variants for the same experiment. Here you see the same information, basically the highest number for each graph, the cumulative CO2 injected for each case, and color coded by also the same property. And on the right hand side, you can see on the x-axis we have number of moles of component of CO2 injected, and we have a CDF showing the relative points as well. So the P90, P50, and P10 are actually calculated automatically. And you can see each individual model put in here along this line. So this is already good, but we are still looking at multiple cases. That's great, but we're still looking at graphs only. So we can keep going through the different possibilities that tNav offers for analysis of the data. Next one would be probably a Pareto chart. You can look at things like field pressure or the amount of solubility, residual, and structural trapping, and how the input parameters affect these 4 different outcomes. And I've ordered it by solubility trapping, but you can also do it by others. Just quickly pick some examples. Caprock vertical permeability affects inversely the field pressure and all the other parameters that we have. So obviously the more vertical permeability in the caprock, the more is actually going away from where we want to store it. Therefore, this makes sense. And you can look at some of the other parameters here as well. So this gives us a very nice, concise view of the impact of the parameters on the important results that we want to compare them to. So far so good, but what about 3D properties? I have 200 runs. How do I look at 3D properties? How do I show my boss maybe 3 maps in a way that makes it easy to understand? Or how do I send the required data to the regulators, which probably ask for some quantiles rather than all the 200 runs? Or things like quantifying plume extent and quantiles as maps. So how do I do this? So we made it very easy to do this in a history matching module, which is let's say the hub for all our uncertainty history matching optimization workflows. If you would imagine n number of cases, and each with its same number of blocks, so we have a particular value at a particular given block for that particular case, and the same. If you keep the block number the same but vary the case number, we can actually get a cumulative distribution function for that particular block. And if we repeat this for all the blocks, then we get a CDF for the whole model, so to say. And from there, we can just keep doing this exercise, continuing to IJK of different values, going through the whole grid. And from there, we can just generate the P10 result, P50 result, P90 result, just by picking it off from where we need to pick it off here. Doesn't have to be P10, P50, P90. You can also pick other quantiles if your regulator requires that, or if your management requires that. So how do we do this? It's quite easy. We actually have a workflow item for this, which looks like this. You just specify the quantile that we want to output and the source property that you have actually previously requested to be output. And if you go into the custom code, so for those of you who have actually played around with workflows in tNavigator, every item actually has a Python code in the background that you can view and modify and edit as you like. So in this case, we wanted to do it for all 3 and not to repeat this. So basically made a copy of it, copy paste, and just change these variables here. So instead of 50, we put a 90 and change the name of the output property. It's quite easy to set up, even if you're not very tech savvy or into Python programming. So from that, we actually generate the probabilistic maps. So on the left-hand side, you can see the P90, in the middle P50, and on the right-hand side P10. And you can see the extent of the plume obviously increasing as the P number decreases. So that's all good. In cross-section, you can also see the same effect. And in this case, we're looking at CO2 molar density. So can we also look at some additional parameters? So what I've just shown seems quite easy. You just take a CDF for each particular block across several 100 cases, and based on the CDFs, you build the quantile that you're interested in. That makes sense. But what about things like plume area, plume extent, distance to fault, or circumferences, and so on? So because everything is integrated, because Marcus nicely passed along not just a data file to me, but the whole project, and because we're both working in tNavigator, I can use all these objects to my advantage. So I can take the maps, take vertical summations of certain properties. I can fit polygons around them. Then I can measure things like the area within the polygon, the largest or smallest length across that polygon. I can do things like distance to fault, as I said. So in this case, we've reported the P90, P50, P10 distances to the fault, so the minimum distance, which usually what is the most interesting. And also moving forward, we can look at some geomechanical properties. So if you remember, Marcus was setting up some geomechanical properties, and that's included in the workflow as well. What we're mostly interested in is obviously caprock failure, but also at the injection site, you might be breaking, so-called breaking the rock, so rock failure. And in this case, we have used more Coulomb criteria. And you can see for 4 different cases here, we have some blocks that actually underwent this failure criteria. So these blocks have already done that, and they're flagged in red here. And how do we actually come up with a probability of occurrence? Just to reduce all of this information to one map, basically take an average. So for each block, we go across all the cases, add everything up, so zeros and ones, and then divide it by the number of cases. And here you can see the final result, which is we call the probability of occurrence. These 2 blocks and these 3 blocks are pretty close to 1 because they're in almost all the cases, whereas these are a little bit less because some have them and some don't. So it's much nicer to look at this than to have to scroll through all 200 cases, let alone try and report it or tell somebody a story around it. So here's some visualization. We can also take the filters as we talked about, or different maps or 3D properties, and use them to our advantage to improve our visualization. In this case, what we've done is taken a property and taken a threshold for it, and everywhere this threshold is true, we have generated a property which then we use to fit a geobody around it. And you can see the geobody sizes moving from P90 to P10. And you can also do the same exercise through 10, just to make it more visually pleasing, if you like. So as conclusion, we know that regulatory bodies require probabilistic assessment of not only the amount and type of trapping, but also spatial properties of the plume. And this is traditionally not too easy compared to the amount and type of trapping, which can be represented in graphs, for example. Luckily, tNavigator offers a fully integrated modeling environment to tackle complex CCS requirements. We have built-in tools which allows for a wide array of reporting options, especially geared towards dealing with large numbers of cases. And integrated workflows allow the generation of any number of probabilistic cases and extraction of required quantiles in an automated fashion. And with that, I'd like to end the presentation for today and move to Q&A.
Thanks, Serkan and Marcus. Looks good. I think we have a few questions that have been coming in, so I'll just have a little look. Okay. Which physics did you use for this model? in general, how do you know which physics to use for which situation? It's a question for Serkan.
Sorry, I was busy with the web. Which physics? So we use CO2 store for this. For those of you that know the different options, there's a few well-known ones like gas watt, CO2 store, and CO2 sol, and you can have different combinations of these. But we thought to keep things simple, CO2 store would be a good one. That includes all four trapping mechanisms, including some built-in reactions. So you're able to generate 3 types of salts as solids, which then changes your permeability and also increases your trapping mechanisms in the mineral phase. But you can use different ones depending on what your needs are. So for a depleted reservoir, I would not use CO2 store. That's meant for an aquifer. I would use CO2 sol. And yeah, I guess we could get more specific, but if the person would, I can get back. Actually, I can see the question here. So yeah, that's the general answer.
Thank you. Next question, can tNav model any CO2 chemical interaction, let's say, with the cap rock if this happens in reality?
Good one. So yes, we can do chemical reactions also within the cap rock. The reason we did not focus too much on this is actually for this demo model, it doesn't occur. So I've actually looked at some of the cases just to double check this. There's some sodium chloride deposition at some point during the simulation, but this doesn't actually stay all the way until the end of the simulation time. So we could actually have another case where we don't stop the injection. We actually continue, and we have different geochemistry or different starting concentrations of your reservoir, and this might actually be possible.
Thank you. I think we'll just do 2 more questions because we're kind of running out of time. I think this one's for Marcus. So how will you update the model when injection and monitoring begin?
Okay, so updating the models. So there's a few cases of real projects out there at the moment, and I think one of the kind of most popular methods for monitoring would be 4D seismic. I know there's others out there as well. But I guess we would take the 4D seismic in. tNav has the capabilities to view our seismic, to do attribute analysis. So you would take those attribute analysis, maybe look at amplitude properties, and then you could create geobodies from this. Any new information that comes in, because we've created workflows that both Serkan and I used, we could update those workflows with any new data, quickly rerun the models. And in the case from the 4D seismic side, yeah, we could create geobodies of those, say, the attributes that define where the plume is, and then compare those to the geobodies created from the simulation, do some kind of assistant history match between the two, and then try and work out which of our models seem to be the most realistic, and then move forward with those models, probably to refine those models to get more accurate results.
Thanks. And I think the last question's for Serkan as well. So can tNavigator handle thermal simulation in cap rock too?
Yes, thanks for that question. I see there's actually a few questions about the cap rock. So if there's anything specific you're asking that I'm missing here, please get back to us or write in the chat or send another question, because I'd like to follow this up. But as far as I know, so the way we do the cap rock is actually it's the same as any other block, just has different properties. So therefore, once you have a thermal option, this is applied to the cap rock equally to as it is done to the flow side, so to the reservoir. So yes.
Thanks. Cool. I think we'll wrap up there. As you said, Serkan, there's a few more questions, but we can follow up personally as well. Cool. Okay. Thank you so much, everyone, for your attention and for joining us. Thank you, Marcus and Serkan, for the presentation. This is the last webinar in our current series, so if you have any topics which you'd like to see us presenting or anything that you want to know more about, then please do get in touch and suggest it, and we'll definitely try and get it into the next series. So yes, thank you so much, and we look forward to seeing you next time.
Thank you for joining.
Thank you.